In the 1890s, a humble British canal engineer by the name of William Smith made an important discovery, which is the foundation of how we tell time in geologic sections today. He was first hired to study the coal fields of southwestern England, near the town of Bath. Then he was hired to survey the excavation of the Great Somerset Coal Canal. At that time, the Industrial Revolution was ramping up in England, and they needed a cheap way to transport heavy loads like iron and coal across the landscape. Wooden horse-drawn wagons on those terrible roads could not handle such heavy loads, so they needed something to transport heavy loads easily from point A to point B. Hutton lived in this house in Tucking Mill, south of Bath, as he surveyed the canal excavations. He got to be very familiar with the sequence of fossils and formations that were exposed in the fresh canal cuts, and began to realize something important. Each formation had its own distinctive assemblage of fossils, and no two formations had the same fossils, so he could tell where he was in the section just by looking at their fossil content. Today we call this the principle of faunal succession. But British geology then was the domain of wealthy gentlemen who did it as a hobby, and they looked down their noses at a humble canal engineer like Smith, who was not in their class. When he visited gentlemen and looked at their fossil collections, he would amaze them with his ability to tell them exactly which formation they'd come from. Naturally, such an important discovery could not go unnoticed for long, and soon other gentlemen were stealing credit from him for his discovery. But late in his life, he published a series of volumes with illustrations of the key index fossils, which gave him full credit for what he had done. By the end of his life, he was recognized as the father of British geology, and his famous 1815 map of the British Isles was called the map that changed the world. The principle of faunal succession not only helped Smith recognize the formations and map all of Britain, but it is now the foundation for the entire geologic timescale. Naturally, such a fundamental principle of geology was not restricted to one place. About 1806, the French anatomist Georges Cuvier and the malacologist Alexandre Bognart were also doing primitive mapping of the Paris Basin in northern France, and independently recognized the sequence of formations and their characteristic fossils around Paris. By the late 1820s, the entire sequence of the geologic timescale was built up by the British and French geologists, and it was no longer possible to believe in a single Noah's flood to explain the entire fossil record. This laid the foundation for what is called biostratigraphy, telling time by the characteristic fossils in the rocks. If fossils change through time and they're best indicators of time, then fossils are the only practical means of telling time in geology. No matter what fads come and go, and what funding agencies do, there will always be a need for paleontologists as long as you need to know how old the rocks are. But there are a few basic rules you need to make a good biostratigraphic collection. First of all, as soon as you find a fossil, be sure to record exactly where you are, not only geographically, but also stratigraphically above a certain marker bed in the rocks, so we know not only where the specimen occurs in space, but also in time. Without that information, the fossil is just a pretty tchotchke, which can be put on a mantelpiece, but has no useful scientific value. If a young field assistant brought a specimen to Morris Skinner, the legendary fossil collector, and did not know exactly where it came from in the stratigraphic section, Morris would toss it over his shoulder and tell him without the data it was useless to him. Once you build up a large collection of fossils, each with their exact stratigraphic position recorded alongside the fossil, you can then plot them up to what are called zones. They mark an interval of time before that fossil existed, during its time of its existence, and then after it was extinct. By combining the range zones of many different fossils, you can then finally subdivide geologic time in any one section. The next task is to correlate the first section with another section at some distance. If you find the characteristic fossils in more than one place, then you can map the range zones across large distances. If you do this with enough sections, you can generate a range zone biostratigraphy. For example, in this illustration, the pink range zone is recognized by a particular type of starfish, followed by the blue range zone, then the green range zone, and then the yellow, and then the pink and orange. The blue one on top is only represented in one section. By the 1850s, biostratigraphy was becoming much more sophisticated, and two scientists, Friedrich Fenstedt and Albert Oppel, decided to use the ammonites of the Swiss Alps as the basis for their concepts of biostratigraphy. From their work, a number of different kinds of range zones are now recognized. You can have a taxon range zone that is defined by the first and last appearance of one particular fossil, or a concurrent range zone, which is based on the overlap of two different fossils. The concurrent range zone is the preferred method derived from Oppel's ideas and finally divides time into very short increments. There are also interval zones defined by two consecutive first appearances or two consecutive last appearances. For a while, something known as an assemblage zone, defined on many different fossils, was a popular method of correlation. However, the top and bottom of each assemblage zone can be imprecise unless you pick a particular index fossil to be the defining taxon at the beginning and end of the zone. In some places, there are huge fossil beds of one particular taxon that are found in many different places. These are often called acme zones or abundance zones. These seem like good time markers, but scientists have discovered that often they are due to local extreme conditions where an animal flourishes and then crashes, rather than a global or even local time event. In specific cases, there are other types of ways of correlating. For example, planktonic foraminifera in deep-sea cores often flip back and forth between right coiling and left coiling, depending upon the temperature in the water at the time they lived. So they can be used to plot up very precise changes in time through deep-sea environments. Whatever you base your bioresonations on, eventually you need to calibrate it to a particular stratigraphic section in a particular place to establish the geologic timescale. For example, the Silurian-Devonian boundary is tied to the first appearance of the graptolite Monograptus uniformis in the Klunk section in what is now the Czech Republic. The Cretaceous-Paleogene boundary, which marks the end of the age of dinosaurs, is tied to a particular section in El Kef in Tunisia, which is marked not only by certain planktonic foraminifera, but also by an iridium anomaly and also by certain isotopic anomalies. These global stratotype sections are the foundation for the modern geologic timescale. There are other challenges and pitfalls as well. Sometimes fossils disappear and then reappear in a local section. These are called Lazarus taxa, after the character in the Bible who apparently rose from the dead. Lazarus taxa are not really extinct, but just vanished from a local section for a while before coming back. Then there are Elvis taxa, which appear to be the same as the original, but are actually secondarily evolved to look like the original species, just like there are fake Elvises running around even after the king was dead. And then there are zombie taxa, which rise from the grave to walk around. These are examples of fossils that have been reworked from older beds and then found in much younger beds at a time when they did not actually live. Not all fossils are equally good for biostratigraphy. Instead, experience has shown there are certain groups called index fossils, which are the most reliable and the most widely used. The best ones are abundant, so you're sure to collect them, widespread, so you find them over a huge geographic region, and rapidly evolving, so you can tell them apart as they change through time. This means that animals that float in the water column, in the plankton, or that swim, the nekton, tend to be the best index fossils. Thus, we use trilobites in the Cambrian, graptolites for the early Paleozoic, foraminifera for the late Paleozoic, foraminifera and ammonites for the Mesozoic, and mostly foraminifera during the Cenozoic. These index fossils are the tried and true time markers through the entire Phanerozoic.